This video is meant to serve as a pretty basic introduction to electricity, and in it I'd like to talk about 4 different things. The first one is sort of a picture of matter that you can use to get yourself quite far in understanding electricity. The next one's about charges, forces that seem to appear around charges, and the idea of an insulator and a conductor. So let's just get right into it then. Let's start by talking about matter first. So by matter I mean any sort of bulk solid object that might look just about anything, something like this, big rock or a piece of wood or metal or glass, doesn't matter what it is, but this is matter here. Now what we get in matter, the reason why it's rigid is because it's made of this very ordered structure inside. I'll just draw a bunch of dots to represent this here. Something like this, just a bunch of dots. And what these dots are meant to represent are the internal structure of the matter itself. And those purple dots can actually be thought of as the nucleus of the material, the molecules, or whatever is in the matter that we're talking about, but there they are. And it's absolutely rigid. These purple dots don't move, they're never moved, they're not expected to, and these can be thought of again as the nucleus right here. So these things are absolutely fixed in there. That's what maintains the structure of the matter itself, nice and solid in there, and you can also think of them as the nucleus. And for this class and most of electricity, we don't really have to get more complicated than that. But even a simpler view of that, you can also just think of these things as the protons inside the material, because the protons are the charges or the objects that are found inside the nucleus of the material. So you can think of those purple dots as the protons. Now, being oversimplifying it here, often there's going to be neutrons in there as well, and the nucleus is a much more complicated thing like that. But for a very basic view of matter, you can think of the protons as being fixed as a solid structure that does not move, and that's the core structure of the matter. Now, of course, interspersed in there, in this bulk of matter, whatever it is, are going to be the electrons. Those are a bunch of little negative things that can be all over the place in there as well. And the electrons are not in the nucleus. The electrons are instead all around the nuclei. Sometimes they can be shared, sometimes they can't be shared. So what this bulk sort of look at matter is meant to represent is the very basic atomic model that you might have in your mind sort of looks like this. A positively charged nucleus with an electron somewhere around it like that, swirling around it or whatever your model may be. The classical model works okay, a little planetary atom. But when we take a bunch of these atoms and put them together like this is exactly what we get. Like if we put Avogadro's number of these atoms inside of this material here, we'll get these protons or these fixed sites here with the electrons going all over the place like that. If you take a bunch of atoms and put them together, the electrons around there might be shared, they may not be shared, but what you are sure about is that the protons stay absolutely rigid, fixed in there. So that's what we mean by matter. Okay, now of course when we have matter like this, let me just remove the little atom right here. When we have the matter like this, the matter can be an insulator or it can be a conductor. And so this will be very important in a class like this, and so the question is, well, what's really the difference between them? Well, the difference between them isn't too big. They both look like this internally, but the part about the conductors is very important here is the electrons here. I'll draw electrons a little E- right there. The electrons are mobile. And in fact, mobile probably isn't the best word here. I should add a little word in here. Very mobile. Okay? So in the conductor, the property that makes them as a conductor is that these electrons here are basically free to move anywhere they want inside the conductor, and they're very easily free and ready and willing to do that mobility here. So oftentimes conductors here aren't really referred as conductors. You can also sort of say that there is a sea of electrons in here. To my mind, I see a conductor like this, and what I think of is like a beehive of electrons. They're all humming around and moving around. They're very easy to move, very easy to influence them, to get them to move around. The protons will stay absolutely fixed, but the electrons are very mobile and will move all over the place in there, and that's what a conductor is there. Very mobile sea of electrons moving around. You can almost forget about the edges right there, and although they constrain the electron in there, just think of it as a big ball of electrons with those little negative charges that are ready to move around at a moment's notice in here. Now you can contrast that with what an insulator does right here, or is. And an insulator, again, looks the same inside, has the protons and the electrons, but the E electrons in there are not mobile at all, not mobile. They just don't move inside of insulators like that, and that's why they're called insulators. They don't conduct electricity. You can't pump current through them. They're just not, electrons just aren't mobile at all. So for the conductors like this, the materials you'd think of conductors, again, sea of electrons, very mobile electrons here. These can typically be your metals. And in a class like this, introductory to electrons, we don't have to get too esoteric with the metals, but you're thinking copper, aluminum, and iron metal. Those are going to be the most common metals that are very good conductors. There's a lot of free electrons in them. The electrons are very mobile, and they move all over the place. Where the insulators over here, on the other hand, are going to be things like glass, plastic, and even wood pops up from time to time in some of these problems and discussions, stuff like that. These are the things that they're certainly bulk, solid. They have the protons and electrons in them, but for whatever reason that the materials are, the electrons in there just don't move around very much at all. They're just not mobile in there. So that's sort of our first stab at looking at some electricity here is matter. Insulators and conductors, the protons are fixed, the electrons are all over the place. If it's a conductor, the electrons can move around very easily. If it's an insulator, the electrons are still there, but they have almost no mobility in the material at all. They just can't move around very much. So the last thing sort of covered here that about this matter here is, well, the types of charges. We've probably already hit them, but we'll just rehash them one more time here just to get it firmed out. We have positive charges and we have negative charges. And oftentimes little circles are drawn around the charges to make them look like little objects like this, and that's the way they'd be here. The most common negative charge that you'll encounter, or the negative charge, is going to be the electron. That is sort of the carrier of negative charges into things here. And you might intuitively, or sort of knee-jerk reaction, think, well, the positive charge is going to be the proton. And it can be in some cases, but I need to caution you about thinking of positive charges as strictly protons, because in our description of matter, we just said that when we had a big bulk piece of matter like this here, that there are these dots in here, which we're calling the protons, and we said that the protons don't move around. So it's very hard to sort of imagine that if something is positively charged, that someone got some protons and put it on some object like that, because the protons don't move around. You can only interact with protons, say, if you go to a particle collider where you can actually start to break the nucleus apart and get the protons out, like the LHC, which runs in Europe. And we're not talking about those types of energies or techniques in this class, so you have to sort of change your thinking a bit to say, well, where do positive charges come from? And positive charges can be protons in some cases here, but in other cases, in most cases, a positive charge really comes from an absence of electrons. So an absence of electrons is really where positive charges come from. And I'll try to illustrate it this way. So it turns out that all matter, that if you just sort of start it or dig it out of the ground, in most cases, we're not talking about anything too weird here, has as many protons as electrons in it. So if I have something like 5 protons drawn in this piece of metal here, for every proton there'll be at least 1 electron like that. And when it looks like this, the matter here is electrically neutral. So although there are isolated areas here where there might be some charge, as a bulk object, like this is a 2x4 from Home Depot, it would be electrically neutral because there's as many negative charges as positive charges in this material here, so it's neutral. So what do we mean by a positive charge can be an absence of electrons? We'll say by some technique, usually some physical technique, by like rubbing on a piece of fur or glass or something like that, I was able to strip a couple of these electrons off of the material. The protons don't move, they're always going to be there. So what type of charge would this material have? Well, it would have a net positive charge now with these things gone. It would no longer be neutral. It would be positive. And the reason why it would be positively charged is because there's 1, 2, 3, 4, 5 protons in there, or 5 sites containing positive charge, and only 3 electrons. So if you get a plus 5 and I subtract out the 3 electrons here, I get a net charge of plus 2. So another way of drawing the material like this would be something just like this, and I would just label it positive like that. It would be a net positively charged material. So you see, it is a net positive charged material, but it didn't come from me adding protons to it. It came from me removing electrons. So that's really the way you should think about positively charged objects here. It's an absence of electrons to balance the positive charges of the protons that are sitting in there. And so that can happen. Now, of course, if I return to the neutral material here that has as many electrons as protons like that, something like this, of course, the next thing I can do is try to add some electrons to it. And I can do that in a variety of ways as well. Usually some rubbing techniques you'll find in the early chapters of this course. Say I added 1, 2, 3, 4 extra electrons to this thing. They're sort of either stuck on there in the case of being an insulator, or mobile, just like the other ones are if it was a conductor. But in either case here, what do I have? I still have my 5 protons in there, 5 protons, but now I have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons minus my 9 electrons. I have a net negative 4. So a way of drawing this material here is, if you didn't want to go so detailed with the protons, just go 1, 2, 3, 4, 4 negative charges on there. You have a bulk negative charge on this material now, so you can do that as well. So the last thing then to discuss then is that the forces that arrive, and those are usually quite simple for people to get because the physics forces that are involved in electricity have crept into our everyday life here, and the force laws are like this. You know them already probably. Opposites are going to repel each other, and like charges are going to attract each other. So yes, if you had two positively charged objects here, again, they can be protons or they can be just materials with an absence of electrons. If you had two positives and you were holding them near each other like this and suddenly you took your hands away, this proton would start to move this way, this one would start to move that way. They would repel each other. The same thing is going to happen if you two have two electrons like this. This one's going to move this way, this one's going to move this way. Ignore that these are here. It's not going to make it that complicated. We're just talking about two isolated charges. They'll probably start to move away from each other. That's opposites repelling each other right here. It's sort of our first force law. You probably know that already. The next one is going to be that like charges attract each other. So if you have a positive charge like this and a negative charge like this, if you hold them like this and suddenly you let them go, yes, this positive charge will feel a force that way, and if it wasn't bolted down, will start to move. This one will start to move that way. So whether they can move or not is a different issue, but they will feel that attractive force towards each other, and eventually they get closer and closer like this. And there's sort of an important idea to think about is what happens when they actually come in contact. So I won't lie, what happens when they come in contact is rather complicated. Okay, but I'll just throw a few of the ideas out there, and I'll tell you the idea you should leave with. If this happens to be a positron and an electron, so a positron is a similar particle to an electron, just has an opposite charge, then what can happen is the two things will disappear, so you won't see them anymore inside this region here, but a little flash of light will have come out. That's one thing that can happen. But again, the interaction is complicated, and I'm not going to pretend to describe it all to you here. But what you should leave with is that whenever you have a positive charge and a negative charge and they get too close to each other, don't worry about the exact physics of what happens when they actually touch or get involved with each other, because it's complicated. But what you should leave with is that when two positive charges either get in very close proximity or you think about them touching, just quit thinking about what actually happens, but you should think about them as neutralizing one another. In other words, they just disappear. So if I have 1, 2, 3, 4, 5 positive charges here, very complicated system, and by some process I brought 1, 2, 3, 4, 5 negative charges near them and drew a red line around them, if I imagine things touching or getting too close together, I can imagine this as net neutral, no charge in there. Either they neutralize themselves, or doing the simple arithmetic I did earlier, for every positive charges, negative charges, but the point is that this is net neutral, or the charges have neutralized each other. We'll see several cases where thinking about charges touching is a good way of thinking that, well, yes, they have neutralized themselves, particularly when we talk about capacitors later on. And so that's what can happen. So those are your force laws for you right there. Opposites will repel, likes will attract, and if two likes get too close to each other, they can physically disappear, a little flash of light will come out, or in the alternative thinking, if they get close to each other like this, and as you back up and think of bulk material, you can think of these things as neutralizing each other or sort of making each other go away, but you can have the same material, but now there's no net charge in there, so it's become net neutral.